You know, in the AI world and honestly in the tech world in general, we've been completely conditioned to believe one thing above all else, and that is that bigger is just better.
Right, yeah, that
Yeah.
has basically been the law of the land.
Like, if you want a faster computer, you get a bigger processor. And if you want smarter answers from an AI, you need a bigger brain. You need hundreds of billions of parameters to get anywhere.
Exactly. The logic has always been that scale equals intelligence. Just throw more compute at it.
But today, we're doing a deep dive into something that really breaks that law. We are looking at a new model called Pixtral 12B. This was just released by the team at Mistral AI.
Yeah, and the headline here isn't just that it's a new model.
Right.
It's that this relatively small model, I mean 12 billion parameters, is reportedly knocking out heavyweights that are nearly 7 times its size. We're talking about it beating things like Llama 3.29 dB on certain tasks.
It's totally a classic David and Goliath situation. But what makes this deep dive so fascinating for you and me isn't just that David is winning, it is how David is winning. It's not about raw power. It's about having better eyesight.
I love that way of framing it. Better eyesight.
Okay, before we completely unpack the whole how part of this, let's set the stage for everyone listening. Pixtral 12B is a multimodal model. We hear that buzzword constantly. What is the functional definition here for our listeners?
Right. So in this specific context, multimodal just means the model doesn't only read text. It sees images.
Okay.
You can feed it a PDF, a photograph, a really complex chart, or, just a messy screenshot. And it processes that visual data using the exact same reasoning engine it uses for text.
So it's reading the world, not just a dictionary.
Exactly.
And we're basing this deep dive on the technical paper Mistral released, plus the benchmark beta that came with it. And I noticed this is an open weight release, right?
It is, yeah.
Yeah.
Released under an Apache 2.0 license.
Which means what for the average developer?
Well, it means unlike GPT-4 or Claude, where the mechanics are hidden behind a corporate API and you never really know what's happening under the hood, developers can actually download Pixtral.
All right, they can play with it.
They can inspect it and run it on their own hardware. And that transparency is great because it allows us to see exactly why it's punching so far above its weight class.
So the core mystery we are trying to solve today is efficiency. How does a 12 billion parameter model beat a 90 billion parameter model? You mentioned Eyesight earlier.
I did.
And I assume most AI models see pretty well by now, right? I mean, I can upload a photo to ChatGPT and it immediately knows what it is. So what's the status quo there?
Honestly, the status quo is kind of like looking through a kaleidoscope or maybe looking through a really thick, distorted glass brick.
That does not sound ideal for precision.
It's really not. We call this the pixels problem. Most current vision models, before they even start to process an image, they mangle it.
They mangle it. How?
Like say you have a tall, skinny receipt from a grocery store, or maybe a really wide panoramic photo of a landscape. Most standard models, like the older GPT architectures or the original Llama vision variants, they force that image into a fixed square.
A square, like a standard size.
Yeah, usually something really low resolution, like 224 by 224 pixels.
Wait, 224 pixels? That is tiny. That's like a thumbnail image from a website in 1998.
Exactly. And if they don't squash it into that tiny square, they chop it up into fixed, rigid tiles.
Okay, so imagine taking a big map and just cutting it into perfect squares with a pair of scissors.
That is precisely what they do.
So if I upload a wide spreadsheet, the model is either squashing it into a square, which would make the text completely unreadable, or it's cutting it into arbitrary puzzle pieces.
Yes, and think about what happens if you cut a word or a critical number right in half, just because that's where the tile ended.
The model loses the context.
Completely.
Right.
Horribly inefficient because you're either losing data through the compression or you're processing a whole bunch of empty white space just to fill out a grid.
It sounds like trying to read a book, but someone has run the pages through a paper shredder first.
That's a perfect analogy. You end up spending half your brain power just trying to reassemble the image rather than actually understanding what's in it.
Okay, so that's the before picture. That is the status quo. How does Pixtral handle this differently? What's the secret sauce Mistral used?
So Mistral built a brand new component from scratch called the Pixtral-ViT.
ViT?
Yeah, vision transformer. Think of it as the optic nerve of the model. It's a 400 million parameter encoder. And its superpower is that it ingests images at their natural resolution and aspect ratio.
Natural resolution, so no squashing at all.
No squashing, none. If you give it a long vertical infographic, it reads it top to bottom as a tall rectangle. You give it a tiny little app icon, it reads it as a tiny square.
It uses a variable number of tokens then.
Exactly, based entirely on what the image actually needs to be understood. It respects the true shape of the data.
I have to be honest, that sounds incredibly obvious. Why hasn't everyone been doing this from day one? It feels like common sense.
It totally does feel like common sense. But mathematically, it's an absolute nightmare to engineer.
Why is that?
Because neural networks love predictable grids. They love being able to say, pixel A is always at row 1, column 1. They want the world to be a perfect, unchanging matrix.
Right. They want structure.
Yes. So when you have variable shapes, you lose that absolute grid. You lose your reliable coordinate system.
So how did the Mistral team solve the math? How do they teach the model where things are if the map keeps changing shape on every prompt?
They implemented something called ROPE 2D.
ROPE, like ROPE, like a lasso.
Yes. It stands for Rotary Positional Embeddings 2D.
Okay, that is a mouthful. Let's unpack that for everyone listening.
Sure. Think of it like navigation. The old way, the absolute positioning, is like using GPS coordinates. You are at latitude X, longitude Y.
Okay.
But if I suddenly stretch the map or cut the map in half, those coordinates are suddenly useless. You're completely lost.
Right, because latitude X might be in the ocean now, or it might not even exist on this new shape.
Exactly. So ROPE 2D is more like navigating by landmarks. Instead of rigid coordinates, it says the library is to the left of the post office, or this specific pixel is diagonally up from that other pixel.
Ah, I get it. So it's relative.
Precisely. It teaches the model the relationship between different patches of the image. It learns that this piece of the chart is directly above this piece, regardless of whether the whole image is 500 pixels tall or 5,000 pixels tall.
It creates a flexible spatial understanding.
Yes.
And that works even if the image is shaped weirdly, like one of those super tall skyscraper banner ads on a website.
It does, because they also use something called break tokens.
Break tokens, how do those work?
Imagine the model reading the image left to right, like a book. When it hits the right edge of the image, wherever that happens to be, it inserts a special digital bookmark.
And that bookmark tells it what?
It tells itself, okay, new row starts here.
So it's essentially saying hit return on a typewriter.
Exactly that. This allows the model to fluidly adapt to literally any shape you throw at it. It scales up for fine print in documents and scales down for simple pictures to save compute power.
So essentially, by not forcing the image into a box, they aren't destroying the data before the brain even sees it. It feels like such a clean, elegant solution.
It really is. And that efficiency is exactly why a 400 million parameter vision encoder, which is actually quite small, can outperform massive ones. It's simply seeing the world clearly while the giant competitors are squinting.
Okay, so that covers the eyes. Let's shift gears and talk about the brain. The paper mentions that Pixtral 12B is built on top of Mistral Nemo 12B. Now, I know Nemo, that's a text-only model, right?
Correct. Mistral Nemo is a highly respected 12 billion parameter text model. It's really well known for being great at coding and complex reasoning.
But usually there's a catch when you do this. I've heard that when engineers take a text model and try to shove visual training into it, the text capabilities actually get worse.
You're completely right. In the industry, we call it the alignment tax.
Or I've heard it called catastrophic forgetting, which sounds terrible.
It is dramatic for the developers who spend months on it. Usually, when you take a perfectly good text model that knows how to code in Python and write poetry, and you shove a bunch of visual training data into it, the internal weights shift.
Right.
The brain gets rewired to handle vision, and oops, it suddenly forgets how to do calculus.
It's like learning a second language and somehow forgetting your first one in the process.
Exactly. But the data in this paper shows Pixtral completely avoided this tax. They ran it through all the pure text benchmarks, so coding, math reasoning, logic puzzles, and it performed almost identically to the original text-only Nemo model.
So it's a true drop-in replacement.
Yes.
If I'm a developer using Nemo right now for my app, I can just swap it out for Pixtral, immediately get vision capabilities, and I don't lose any IQ points on my standard text tasks.
That's the claim, and the benchmark data backs it up completely. That is a huge deal for adoption, because nobody wants a model that sees better but acts dumber. You want the best of both worlds. Plus, they give it a massive context window, 128,000 tokens.
128K context. For our listeners, that's roughly the length of a small novel, or maybe a really dense college textbook. But we're talking about images here, so what does 128K allow you to do with visual data?
It allows for multi-image reasoning. You aren't limited to showing it one single photo and asking, what is this? You can dump an entire stack of documents on its desk.
The source material had a really cool example of this that stood out to me. They showed the model two separate images. Both were tables of data, but from completely different files.
Right, one table was, say, Q3 sales data, and the other was Q4 projections.
And the prompt simply asked the model to merge these two images of tables into a single markdown format table.
Which is a task that would trip up a lot of humans. You have to read table A, remember the numbers, look at table B, align the corresponding columns, and then perfectly format the output. It's incredibly tedious.
And Pixtral just nailed it.
It nailed it perfectly. Because of that natural resolution we talked about, it could read the fine print in both tables without any blurring. And because of the 128K context, it could hold both images in its working memory at the exact same time.
It's reasoning across the images, not just looking at them in isolation.
Yes, exactly.
That capability alone feels like it solves so many administrative headaches for businesses. But speaking of reasoning and testing, this brings us to probably the most controversial, or at least the most dramatic, part of the paper. Section 3, the benchmark crisis.
Oh, this is fascinating. This is where the Mistral team throws a little bit of shade at the rest of the AI industry.
So they're testing Pixtral against the giants, Llama, Qwen, Gemini, and they realized that the current scoreboard was kind of broken.
In a major way, yes.
Yeah.
While testing, they found that a lot of the so-called failures from competitor models weren't actually failures of intelligence at all. They were failures of stubbornness.
Stubbornness, like a defiant teenager.
A little bit, yeah. Imagine a standard benchmark question. Shows a picture of a cat, and the prompt says, is this a cat or a dog? Answer A for cat, B for dog.
Simple enough, a multiple choice question.
The correct answer is A. But a competitor model like Llama 3.2 might reply, the answer is definitely A because I clearly see whiskers and pointy ears.
That's a correct answer, a very helpful answer, actually. It shows its work.
To a human, it's a great answer. But the automated grading script running the benchmark is only looking for the single character A, just the letter.
Oh, I see.
So because Llama added a totally helpful sentence of explanation, the grader marks it as completely wrong.
That seems incredibly petty. You failed the test because you were too helpful.
It is petty. But unfortunately, that's how we measure these things at massive scale. So Mistral did an experiment to prove this. They reran the benchmark tests using what they call explicit prompts.
What does an explicit prompt look like?
They basically yelled at the models in the instructions. They said, answer with a single letter. Do not explain yourself. Just give me the character and nothing else.
And I assume the competitor's scores suddenly went up.
Drastically. When forced to use specific formats, models like Llama 3.2 and Qwen 2VL suddenly looked much smarter on the scoreboard. But here's the big flex for Mistral.
What's that?
Pixtral didn't really need the help. Whether the prompt was super vague, what they call a naive prompt, or strict and explicit, Pixtral performed consistently well.
So it just has superior instruction following. It naturally reads the room better.
Exactly. It understands the actual intent of the question, not just the literal keyword match. It figures out what the user really wants.
But Mistral realized that just fixing the prompts wasn't enough to solve the bigger issue, right?
Right. They realized the tests themselves, these simple multiple-choice visual QA tests, just don't reflect reality. No one uses a highly advanced AI just to play multiple-choice quizzes.
Right, we have conversations with them. I don't hold up a complex financial chart and say A or B. I say, look at this chart. What does it mean for my Q4 strategy? And why is that one specific bar so low?
Exactly. We ask open-ended questions. So Mistral created a brand new benchmark to reflect this. They call it MMMT Bench.
MMMT Bench. What does the MT stand for?
Multi-turn. There's a multimodal, multi-turn benchmark. It completely moves away from single-question quizzes and simulates a real-world back-and-forth conversation involving charts, PDFs, and diagrams.
But how do you grade an open-ended conversation? You can't use a simple answer key for that.
You have to use a judge, specifically an LLM judge.
Okay, so another AI is grading the AI.
Yes. They use a massive model, like GPT-4, to read the entire conversation between the user and Pixtral, and then the judge grades the answers on a scale of 1 to 10 based on helpfulness and accuracy.
That sounds a bit meta, but I guess it makes sense.
It's becoming the industry standard, because it's really the only way to measure nuance at scale. And importantly, Pixtral crushed this new benchmark.
And does that LLM judge score actually match what humans think?
It does. The results correlated highly with the LMSE's chatbot arena, which is where actual humans blindly vote on which model gave the better answer. So this new metric actually tracks with real human preference.
Okay, let's get out of the theory and look at what this actually looks like in practice. We've talked about the architecture and the benchmarks, but I really want to know what this looks like for an everyday user.
The paper highlights a few specific use cases that are really telling.
Yeah, let's start with the job security chart. That one was fascinating.
This is a perfect example of real multimodal reasoning. It was a complex bar chart showing anxiety about job security in the U.S., what they call job jitters, and the data was sliced up by generation.
Right, it had Gen Z, millennials, and boomers, lots of bars, lots of very similar colors. It looked like something that would be incredibly easy to misread if you were just skimming it.
Exactly.
Hmm.
And the prompt asked the AI to analyze the trends. The competitor model, Gemini Flash 8B, which is Google's highly efficient model, actually hallucinated.
It got the data wrong.
It got the data completely wrong. It confidently stated that certain generations were worried when the charts show they weren't. Another model, Quenvio, gave an answer that was technically true but way too vague. It basically just described the colors of the bars without providing any insight.
And what did Pixtral do?
Pixtral acted like a senior data scientist. It correctly extracted the specific numbers first. It noticed that 82% of boomers were not worried at all, while Gen Z had the highest anxiety.
So it read the numbers accurately.
But then it went a step further and synthesized the insight. It explicitly stated there was an inverse relationship between age and job security concerns.
See, that's the difference between basic OCR, just blindly reading text off a page, and true understanding. It actually connected the dots.
Correct. It didn't just read the chart. It interpreted the story behind the data.
There was another example in the source material that I think every web developer, or really anyone who has ever had an app idea, is going to love. The image-to-code example.
Oh, the napkin sketch? Yes, the ice
Yeah.
cream app. That was incredible.
Yeah, walk us through that one. They literally took a hand-drawn sketch, just scribbles on a piece of paper of a website interface.
Right. The title scribbled at the top was Pick an Ice Cream Flavor.
Yeah.
And it had a very rough drawing of a drop-down menu and a Next button.
And they fed this rough, messy image to Pixtral and asked for the HTML and CSS code to build it.
And Pixtral generated perfectly working code. Not just a static, dumb image of a website, but functional logic.
It actually worked.
Yes. It included a fully functional drop-down menu with options like vanilla and chocolate already coded inside it, perfectly replicating the intent of the scribble.
That is huge for rapid prototyping. I mean, you could whiteboard a concept in a morning meeting, snap a photo with your phone, and have the skeleton code up and running 5 minutes later.
Exactly. It bridges that frustrating gap between design and development significantly. It translates a visual idea directly into structural code.
And the last example I want to highlight really proves the value of that natural resolution technology we started the deep dive with, the global GDP chart.
Oh, the pie chart map hybrid. That was an absolute nightmare of a visualization.
Yeah, whoever designed that chart in the real world needs a stern talking to. It's a pie chart where the slices are color-coded by global region, but it's also overlaid on a map, and there's tiny text scattered everywhere.
It is visually chaotic.
Yep.
And the task they gave the model was, list the top 5 countries in Europe with the highest GDP.
Think about the logical steps required there. First, the model has to find Europe by looking at the color key. Okay, Europe is the green color.
Right.
Then it has to scan the whole messy chart, actively ignore the red and blue slices, find the green slices, read the incredibly tiny numbers inside those specific slices, and then mathematically sort them.
It's a lot. And if you were using a standard model that squashes all images down to 224 pixels, the green color key might get completely separated from the slice, or the tiny text would blur into unreadable gray pixels.
The data would be destroyed.
Exactly. But Pixtral saw it in high fidelity because of its natural resolution.
Yeah.
It easily identified the green region, extracted the right countries, and sorted them perfectly.
It really proves that it's strictly a vision test at that point. If you can't accurately see the pixels, you can't do the math.
And that is the absolute crux of it. The model didn't necessarily need to be smarter or have more parameters. It just needed to see better.
So bringing it all together now into Section 5, performance, where does Pixtral 12B ultimately sit in the hierarchy? You mentioned early on that it punches way above its weight class. Who is it actually beating?
Based on that MMMT bench we discussed and the human preference on the LMS arena, it is consistently beating Claude 3 Haiku and Gemini 1.5 Flash 8B.
And those are the go-to highly efficient models from Anthropic and Google, right?
Yes, those are major billion-dollar corporate models. Beating them is incredibly impressive for an open-weight release.
But there is a bigger headline here.
There is. The real headline, the one that should make everyone in the industry pause, is that Pixtral 12B is statistically comparable to Llama 3.2 90B and Qwen2 VL 72B.
Let's just pause on that for a second. 12 billion versus 90 billion. That is a massive, massive difference in size. What does that actually mean for the end user?
It's a massive difference in cost, speed, and energy consumption. Running a 90 billion parameter model requires really expensive server-grade GPUs. You're talking thousands of dollars in hardware or significant ongoing cloud costs per hour.
It's out of reach for most people.
Exactly. But Pixtral 12B, you could theoretically run this on a high-end consumer laptop or a single gaming GPU you have at home.
That completely democratizes the tech. It means a small startup or a college student or an independent researcher doesn't need a massive Silicon Valley cloud budget to have state-of-the-art multimodal AI capabilities.
It provides what is currently the best performance-to-cost ratio available in the open weight category, period. It makes high-end vision AI accessible to almost anyone.
So what does this tell us about the future of this field? Because we've been in an era where every single new model release just boasts about being larger. More parameters, more training data, massive data centers. Does Pixtral signal a real shift?
I think it proves that we've been, frankly, a little lazy with our data.
Right.
We assumed that to get a smarter AI, we just needed to build a bigger brain. We just threw more raw compute power at the problem.
Brute force.
Exactly. But Pixtral shows that the architecture, how you actually process and respect the inputs, matters just as much as the sheer size of the model.
It's not just about the size of the engine, it's about the quality of the fuel you're putting into it.
Or rather, how the engine intakes that fuel.
Yeah.
By respecting the natural resolution of images, Pixtral manages to get way more intelligence out of far fewer parameters. It's optimizing the input rather than just blindly expanding the processor.
It's a really compelling argument for quality over quantity in AI development.
It is. And honestly, I want to leave you, the listener, with a provocative question that this paper raised for me. It's something I haven't been able to stop thinking about since I first read it.
What's that?
If a 12 billion parameter model can tie with a 90 billion parameter model just by fixing its eyesight, just by not squashing the pictures it looks at, it really makes you wonder about all the other major models out there.
How so?
Think about it. How much actual intelligence are we currently losing in our top-tier AI models simply because we're feeding them the data in the wrong shape?
Uh-huh.
Are models like Llama and GPT actually much smarter than we think they are, but they're just being hampered by blurry, compressed vision?
That is a wild thought. Are we mistaking a need for bad glasses for a lack of intelligence?
Exactly. And if we fix the input mechanisms for other types of data too, like audio, video, or spatial robotics, do we really need to keep building bigger supercomputers? Or do we just need to stop squashing the data? Maybe the future of AI isn't just bigger models, but clearer perceptions.
Efficiency might truly be the new frontier. A huge thanks to the Mistral team for open sourcing this work so we can actually see how the sausage is made.
It really is an exciting time to be watching the code itself, not just the finished products.
Absolutely. Thanks for joining us as we unpack all of this. We'll catch you on the next deep dive.